introduce our guest today, Dr. Shi from Stanford University. So, Carl.
Hello, thank you, Dr. Pan. Um, Allow me to introduce myself. My name is Carl Ho at the University of Texas at Dallas. I want to say good morning to our guest in Taichung, Taiwan, ROC, and also our guests in the US from maybe other continents too, and say good evening or good afternoon, and to those who are in the United States. And I'm really pleased that we start this fourth season of the Colloquium. Now this is the inaugural. This is the first talk and the Colloquium bring to our audience, and we are really honored to have Dr. Yiqing Xu and Professor Xu. And in my introduction, I only gave a really brief bio, but here I would like to give you a little bit more about Dr. Xu. And Professor Xu is an assistant professor in Department of Political Science in Stanford University, and he actually taught in University of California, San Diego too. And so he has a really impressive record of publication and research. He's so dedicated in doing research in political methodology and Chinese politics, and excuse me, and particularly as in some innovative methods and approaches in studying difficult phenomena and difficult data. And he is also a faculty affiliate in the 21st Century China Center at UC San Diego, and also Stanford King Center on Global Development, and Stanford Center for East Asia Studies, and Stanford Causal Science Center. So, and he's not substantively prolific, but also methodologically prolific too. His work had appeared in basically all the journals and in a top caliber, and American Political Science Review, American Journal of Political Science, the Journal of Politics, Political Analysis, Political Science Research and Methods, and Journal of Development Economics, and among many other peer-reviewed journals. And another thing I must mention to you is he is really well noted. His research is receiving multiple awards, particularly the prestigious John T. Williams Prize by the Society of Political Methodology. He has won the Miller Prize for 2 times in 2018, 2020, and for the best work appear in Political Analysis, which is one of the top journals. And if it is a political methodology, it's a top journal, and not one of these are top. And he also won the prize and as the best article award from American Journal of Political Science, and also he also won the paper as the political analysis editor's choice in 2017. So today we are really privileged to have Dr. Xu and
对哈，行政人员才有。我今年只有编，到年底只有编2笔而已。不过你不是第1名啊。
Okay, sorry. All right, and without further ado, allow me to introduce Dr. Xu, and his presentation, his speech is on two-way fixed effects models, recent criticism and remedies. Dr. Xu, please.
谢谢侯老师，谢谢潘老师。Thank you, Professor Pan and Professor Ho. The honor is mine. I'm really privileged to be able to present you some new findings on an old topic today as a first, I'd say, inaugural, as you said, talk this year. But I know this colloquium has a long history and has been benefiting many students and scholars in the field, spreading knowledge in not only political methodology, but also substantive work and their combinations. I'm really honored to be part of it. So I have to apologize for two things I said earlier to Carl. So one thing is kind of minor is that I have a 2-monitor setup. So I'm actually looking at your comments in the chat if you have any. Sometimes from time to time I'm looking away from the main camera. It's because I'm looking at whether you have any questions. Second is actually more about my throat situation. I caught COVID in January, so until now I still have a lingering cough. It's like post-nasal drip causing cough. So it's nothing serious, but it's just really annoying. When I speak more, I start to cough, and if I don't speak, I don't cough. So that's the situation. If you would tolerate me. Okay, so let's get to the cut to the chase about today's topic. So. If you look at the title, it will be really, you would ask yourself this question: why should I be here? Why should I be listening to this talk on TWFE model? This is a model that is ubiquitous in today's social sciences, and we were taught by our professors about this model. If not in the first quarter, in the first semester, must be in the first year. You learn about this model, and in programs like Stata and R, it's extremely easy to estimate, right? So in old days, we use XGRAG, and nowadays you use RAG HDFE in Stata. And in R, you have a set of packages that help you to estimate TWFE models. So this is something that every grad student or even undergrad students can do on their computer. And I'm quite sure like 80% of you have estimated TWFE models. So why should we discuss this? I think the reason is because there have been a lot of reflections recently in the not only political methodology, in the econometrics community, statistics community, and political methodology community about the credible usage, the correct usage of TWFE models. So I'm going to talk about these developments in the literature, and we're going to talk about knowing about these problems. What should we do as an empirical researcher? So this talk will be really applied. So I think that suits the goal of our curriculum well. Okay, so motivation. I want to start with two facts. One is something I've already mentioned. It is everywhere. This panel data are everywhere. I think mostly because in social science we are tempted to conduct causal analysis. We want to do causal inference, although descriptive inference is also very important, right? We want to describe things in a correlational way, and many of these type of descriptive work are published in top journals as well. However, a large chunk of our effort is devoted to establishing causal relationships, and the causal relationships are difficult to establish if you don't run experiments, right? If you run experiments, it goes standard, but people argue that they may have limited external validity, they're expensive to run, sometimes they're unethical to run, right? So if you want to study the effect of smoking on health, it's unethical to assign cigarettes to subjects, right? That's why causal inference is difficult to do. If you don't use experiment as a gold standard, what can you do? So in the past few years, the so-called credibility revolution, represented by scholars like Angus Imbens, Carl Kruger, like the Nobel Prize laureates in 2021, and his famous textbook, Angus Pischke, we basically learned, okay, we can establish causal relationship using IV, instrument variables. We can do regression discontinuity designs. I'm sure the speakers before me have talked about these methods, but oftentimes it's difficult to find credible IVs, right? Angus.
Sorry, Yiqing, somehow you got muted, and let me check if there's something on my side. Accidentally mute yourself.
Okay, does that work now?
Yeah, good.
So weird.
Thank you.
Okay, so where am I? So I'm talking about we can use RD and IV, but yeah. RD and IV are difficult because IV are difficult. Good instrument variables are difficult to find. So I'm listing experiments, right? or RCT, and you may also have instrument variable, you have RDD design. These are very good research designs that scholars use to establish causal relationships, but good IVs are difficult to find. A good RD design is difficult to come up with. Sometimes you have like elections, then you can use election-driven IV, and sometimes certain policies are dependent on population size. Then you have this kind of kink that you can take advantage of. But these are difficult. That's why the next best thing that people can do are using methods related to panel data. These include difference in differences. This includes two-way fixed models. And in more recent years, there are usage of synthetic control methods, which I also am very interested in studying. So that's why so many scholars study panel, use panel for their analyses, and that's why I'm very interested in panel data. I'm especially interested in doing causal inference with panel data. So just to illustrate what I just said, if you look at the number of papers published in top 5 journals in political science, panel paper, there are more and more panel papers. This is based on a Google Scholar search. Difference in differences in a panel setting and fixed effects models in a panel setting. Okay, a lot more papers are published using these methods. So in our review, so we basically what we did is to look at all the past 5 years. We start from past 5 years, and then we extend to past 6 years. Since when we were writing this paper, another year passed. We look at the past 6 years, and every paper that has used panel data. Panel data are longitudinal data, right? You have a unit dimension, you have a time dimension. You're following the same unit for a repeated period of times. You have repeated measures of the same unit, following a unit for a period of time. So for all the panel papers, 77%, a vast majority of them, use some kind of fixed effect models. What's the rest? The rest maybe maybe it's IV, although the data are panel, but you're using IV, RD, or nonlinear models, or sometimes lag-dependent variables without fixed effects, but they are a minority. Most papers using fixed effects, and close to 60% of these papers using two-way fixed effects. That's just how prevalent two-way fixed effect models are among the papers that use panel data or longitudinal data. That's based on the data papers published in political science. The second fact is that there have been a lot of literature discussion about the validity or the suitability of using fixed effects and two-way fixed effects estimators in social science settings. It came from several different directions. The first one, I don't know, maybe most of you are not old enough to remember this debate. This debate happened in political science when political scientists like Don Green started to introduce fixed effect models. At that time, it's mostly unit fixed effect model from economics to political science. And then there's reaction to such introduction, and people say if you use fixed effects, you're throwing away a lot of information. You're throwing the baby with the bathwater is the title of one paper. So there's a debate about whether fixed effects are necessary to be controlled for in a model. I think the end of the debate, although I think those scholars who argue that fixed effects may be too stringent, this model may be throwing away a lot of information, has a higher win the debate. It's hard to say, right? Who wins the debate, but the result is most papers keep using fixed effects models. So at the end of the day, I think mostly affected by the prevalence of two-way fixed models in econ. Political scientists basically follow up with these type of two-way fixed models. Another set of studies by mostly economists or econometricians. These are applied economists. These are econometrician Cameron. They argue in DID or fixed effect models, if you don't use cluster standard error, or if the number of clusters is too small, you may underestimate the variance of your coefficient. And that's very well known. So in today's seminars, if somebody presents a panel paper, somebody would probably ask the speaker, if the speaker doesn't preempt that kind of questions, have you clustered a standard error? The origin are these papers. Like basically, if you don't cluster because of the correlation within a unit or within groups, a Hilbert-White standard error would vastly overestimate the precision or underestimate the standard error. Then you have a lot of stars, you publish a paper, but you actually don't have that much variation. Your standard error should be much bigger. That's a set of problems that's well known. These two are well-known problems, but in the past 5 years, there are two other important criticisms about TWFE models. One is more from the design perspective, is more connected to the causal inference literature, which puts a lot of weight on design. Design means your understanding of how treatment is assigned, right? Mostly, of course, there are other issues like interference and the model for potential outcomes, but you want to have a clear understanding of the mechanism of treatment assignment to have a strong design. This design, the word design in causal inference or statistics is related, but not exactly the same as our usage as in research design. You want to have a research design that has a strong design component, meaning that you want to have either directly manipulate the treatment assignment mechanisms or have a lot of understanding of how selection or how treatment assignment happens. And these authors argue, there are more, I just quoted a few. These authors argue that for fixed effect models, actually our understanding of treatment assignment is very limited. When you write down outcome model, you actually are kind of agnostic or assume away the design problem. A different issue which raises a lot of tension, attracts a lot of tension in the econometrics literature, and all these papers are published in top journals in poli-sci and economics or econometrics, AER, JOE, Journal of Econometrics. This paper this year published in RES, and also from Koski and Insong in AJPS. So these papers are about whether the fact that the treatment effect is not homogeneous, is not constant, the fact that the treatment effect is heterogeneous, what are the consequences for our two-way fixed estimates? That's the question being asked. I will discuss this in more details later. Okay, these two sets of, so putting here, these two sets of concerns are the focuses on HTE, on heterogeneous treatment effect. Scholars, they point out the problem, and they propose remedies. They propose estimators that they believe are solutions to this problem. And because there's so many papers, there are a lot of estimators. Then as an applied researcher, we are confused because we don't know which estimator should we use in our applied work, right? That's a that's a very common problem. So in the past few months, maybe up to a year, many students knowing about the development of this literature came to me and asked me about the right type of estimator, the right estimator they should use, the best estimator they can use for their applied work. That's a question that needs to be addressed. And we want to address in this talk as well. Okay. All right, so let's get a quick review of the two-way fixed effect model. When we say two-way fixed effect model, there are two different concepts. One is the model, one is the estimator. Right? Estimator is just a machine. It's a function. You give data to the function, it outputs some number. Right? Just like ORS is a estimator. Right? It's a machine. It's a x prime x inverse x prime y. It's ORS. Right? You give it data, and then it gives you a beta coefficient. But whether that beta coefficient is meaningful relies on your belief of the model and your belief of the assumptions. So here I'm talking about not only the estimator, but also the model that researchers often assume when they conduct applied work. So this model actually has two components. The first component is the functional form component, which usually is written this way. So you have this D represents the treatment indicator. It's binary. So in this talk, we will focus on the binary treatment because that's a case where we understand very well. Continuous treatment, there's insufficient number of work devoted to continuous treatment. It's a more difficult case. And these are the covariates, and we have additive TWFE effects. Okay, these are the outcome model that we often assume in applied work. If you just open an APSR or open a applied econ journal, you will see this kind of models everywhere, right? Some are maybe slightly different, but very similar to this one. So when we write down a TWFE model, these alpha and the Kasai T, they're not observed, right? You're basically adding a bunch of dummies, time dummies, unit dummies, or you use a demeaning algorithm to remove them. But we assume they exist. There is some kind of a heterogeneity. It captures unit and time heterogeneity. And then when you write down a TWFE model, you also assume strict exogeneity, which is a very strong assumption. That's why the strict is there. It assumes that the treatment assignment vector is independent of the error term. As you can see, these two assumptions are closely connected because the error term is only well defined when you believe that this linear model is correct. All right, so note here we have 4 subscripts. The IJTS means that my assignment, the entire vector of assignment is orthogonal to not only myself, the entire vector of error terms, and also my neighbors and other people's error terms. So you can write it as a vector. These two vectors are this is bold. Vectors are completely independent, conditional on a bunch of stuff. Well, you don't have to condition because the error term is already have conditioning inside, and that's a very strong assumption. Okay, so what does this combination of assumptions entail? So from today's perspective of causal inference, we can break down these sets of assumptions, this combination of assumptions, into 3 parts. Or some people may argue 2 parts, but I can break them down into 3 parts. The first part is on assignment. So how the treatment is assigned. And if we look at this DAG, this is a DAG. This is a causal graph that is consistent with the strict exogeneity assumption. Let's go a little bit slower. So here we have the D, right? D is the treatment, and the Y is the outcome. We are interested in the effect from D to Y, right? From D to Y. It's a contemporaneous effect. Okay, and then what we allow covariates, right? We allow covariates X that is kind of exogenous. We can have exogenous time varying. These are time varying covariates to affect Y. And these X are observed. These black circles are solid circles are observed. These white hollow circles are unobserved. Okay, and we are different from a cross-sectional setting, from ignorability setting or selection on observable setting. We also allow time varying confounding. Okay, so that's what's special about TWFE effects. TWFE effects actually allows confounding, right? In a cross-sectional setting, we do not allow confounding. We rely on ignorability, meaning that everything needs to be controlled for to remove selection have already been observed and controlled for. That's selection observable. But TWFE models, the panel model actually allows unobserved confounding. These U's are U, I, T. Well, I omit I here because this is just looking at one unit. So you imagine there's an I for every notation. So you actually allow UIT minus 1, UIT plus 1 to exist. But that's really counterintuitive, right? So for causal inference, how come I can allow unobserved confounding? If I have unobserved confounding, it means that it's correlation, it's not causation. It's confounded by this set of variables. then the functional form come to the rescue, right? Basically, the trade-off, the cost is of control of like a account for such confounding is that you need this confounding to be able to express as a additive combination as summation of two components. So it needs to be following a particular functional form, specifically a additive functional form. So the confounding needs to be either not changing with unit or applied to everybody the same. Common time shock, that's fine, or time invariant variables, that's fine. Okay, that is very well known. I'm just interpreting in a different way. But when you use TWFE model, most people will say, okay, the advantage of TWFE model is that I can allow confounding, especially I can allow this kind of alpha I, which is time invariant confounding. Any confounder that does not change over time, it will be canceled out. But that's actually based on a functional form assumption. The problem with this kind of additive functional form is that it's scale dependent. Sorry. It means that when you change the scale of y, this assumption will change. When before transformation, maybe it holds, and after transformation, it doesn't hold. A simple example is taking a log. Taking a log as transformation scale change, then assumption may not hold anymore. Okay, so let's look at the graph again. Let's ask ourselves what arrows are missing from this graph. The missing arrows are something being ruled out by the combination of these two assumptions. This combination of assumptions. So one obvious thing that is being ruled out is the carryover effect, right? So basically, today's treatment can affect future outcome. That is being ruled out. That is not so crucial, so we can relax this assumption later. I just want to let you know that in most applications, when you write down this model, when you don't add lag terms, some papers add lag terms, so YIT minus 1, right? So this is basically saying, oh, yesterday's treatment status may affect today's potential outcome. So you kind of, in a parametric way, allows carryover effects. This is called carryover effects. Carryover, 延续效应. Okay, that is not allowed if you write an outcome model like this. What is not allowed in addition? Okay, we do not allow feedback, right? We do not allow that past outcome or past covariates to directly affect future treatment assignment. That is what we call the feedback. Right? Feedback effect. Feedback effect is not allowed in fixed effects. And this is a key contribution of Koski and Insong's paper. They point this out very clearly. Okay, so when does feedback exist? Right, when it's very hard for us to believe that feedback does not exist. A very simple and common case is doctors giving drugs, assigning drugs to patients, right? When doctors give you medicines or drugs, obviously the assignment is dependent on your health condition yesterday, right? If you feel better, the doctor will adjust the medicines that they will give you. If you feel worse, they will also adjust. That is a feedback. That means that your outcome is directly affecting assignment next day. That is also called sequential assignment. Sequential assignment is ruled out if you use TWFE stress models. All right, so I can write sequential assignment. Okay, that's the first set of assumptions on how the treatment is assigned. TWFE model already limits the type of assignment, the type of hypothetical experiments that we are running. We think the model is, so the DGP is produced by. The second set of assumptions is what we call SUVA, is interference. SUVA is stable unit treatment value assumption. You can understand when you learn causal inference, you kind of know SUVA has two components. The first component is that the treatment is well defined, right? If we're doing a drug test to see whether this drug is effective in curing a disease, the drug only has one copy, only one type of drug. If the dosage are different, these are two different types of treatments, right? This is the first component. The second component is that there's no interference, there's no spillover. If you are studying vaccine in a observational setting, obviously there are spillover because vaccine affects other people's your treatment status will affect other people's potential outcome. But when we write down this outcome model and assume strict heterogeneity, we have already assumed away spatial spillover. So no spatial spillover, no anticipation effects, no carryover effects. I talked about carryover early. So in this graph, the anticipation effects is future treatment affects today's outcome. Carryover effects is what I just talked about. Today's treatment affect future outcome, right? For policies effects, it's very common to have anticipation effects, right? I know there's a tax increase on what day the law has been passed, and then the law will be effective on that day. And prior to that law, we do something. We buy a car before the tax on car increases, right? That's anticipation effects. And policies also need some time to show its effectiveness. That's carryover effect. You cannot assume that the policy will be immediately effective, right? Some changes will be immediately effective, but not others. Okay, the third set of assumptions is on constant treatment fact. You can understand both assumptions as models on potential outcome. Both are restrictions on potential outcome. This is on how D is assigned, how treatment is assigned. All right, so this is very straightforward. Basically, you assume this effect D on Y is a constant. It does not change over time. It does not vary across units, right? A and B, they get treated, or different localities gets a policy, the same policy, but their effectiveness is exactly the same. That obviously is a very strong assumption, right? In the experimental world, if you remember experiments, we don't need to assume constant facts. Experiments is purely non-parametric. We use difference in means estimator to get ATE. We allow the treatment fact to be arbitrarily heterogeneous. Okay, a lot of discussion on negative weights will be around the constant treatment fact assumption. Okay, so what did I do? It's really straightforward. It's basically we reinterpret, there's nothing new here. We reinterpret these sets of assumptions from today's causal inference language in a very simplistic way. Three sets: assignment and models on potential outcomes, including SUVA, and including the effect, whether the effect is constant or not constant. And another side note, I'll pause after finish these slides because it's important to know whether you have questions. Strict heterogeneity directly implies parallel trend assumption, or PTA. I'll use PTA throughout the talk. Parallel trend assumption is written this way. Sorry, there's a conditioning here. Why didn't it show up? Conditioning on observables, and for each unit I or J, the non-treated potential outcome over time, from time T to time S, their expectations are the same, right? That's parallel trends, right? Most of you have seen the parallel trends graph, so I wouldn't do that again here. So that's to keep in mind. And parallel trends is weaker than strict heterogeneity, but in practice, we kind of don't distinguish them very often, because they are kind of observationally equivalent. Okay, so I'm going to pause a little bit and sip some water and then see whether you have any questions.
Sure. Dr. Xu, and we have a couple of questions in the chat, and I can read it out. And so in case for those who do not have access to the chat box, and the first question is, if we can know the high-level agenda, I think maybe referring to the earlier slides and about I think this question may be asking about before the assumptions, that what are these trying to expose. And I think you mentioned that in you elaborate about this two-way fixed effect and models. Then I think another question, a follow-up question is clear, and hope I can have clarification on functional form assumption. I think, does it mean that the outcome variable and the covariates should assume the same functional form? Okay, I think I think I briefly explained that when it go across time. Maybe we can go one more time. So please feel free to ask follow-up questions, and if you need to ask more, okay? Let Dr. Xu and go ahead to talk about
functional
this.
Form. So when we say functional form, we mean the functional form of y, basically. How we it's called response function, right? So how y respond to treatment. Yeah, we don't attempt to explain x. X are the covariates that we assume to be orthogonal to the error term, although they can be correlated with the fixed effects. In terms of today's agenda, so this is a long introduction, but what I plan to do is to before this roadmap, to give you a review of what TWFE effect means. Although most of you would think this, I know this very well from grad school, but this causal inference perspective is kind of new, is newish to a lot of people, so it's worth to review them and to decompose everything and make it very clear. And then I will go back and then talk about the consequences of violation of parallel trend or violation of strict homogeneity and the violation of constant treatment effect, and give you a overview of what the literature, the recent literature concerns are. So we need to understand what their concerns and then seek remedies, right? So I will explain these concerns. And then after I explain the concerns, I will talk about these new methods proposed by the authors of these papers. There are 6 different estimators, so I will summarize all of them, and then I will report a finding or some findings from a large replication effort that I've done in the past year with students. So basically, we replicated a series of papers, over 50 papers, and then we report results for 37 papers. And then using these papers as examples, I will give you some recommendations how we can proceed later. That's my plan today. Okay. I'll come back to, hope this answers your question. Okay, so keep in mind we have these three sets of issues with this model. Okay, so now remember, if you still remember, in the more recent literature, we're concerned about assignment, we're concerned about HTE. Let me first talk about HTE. All right, this is the famous Goodman-Bacon paper, the TWFE paper. You may or may not know. If you don't know, it's totally fine. I'll explain to you what this is. The question the literature is asking is whether a TWFE estimator. So you have this panel data. You run a TWFE model. The series or methodologists are asking whether these kind of models can get you some kind of convex combination of the individualistic treatment effect. There's a lot of jargons here. Basically, it means, let's say each unit, each observation has a treatment effect on top of it, right? And then we hope that our TWFE effect coefficient can represent is a convex combination of these individual effects, because if the weights are not convex, it's possible that every observation on top of it, there's a positive effect, but you end up getting a negative coefficient. That's really bad, right? So the literature is pointing out a possibility that these weights may not be, that because of the weights problem of coming from heterogeneous treatment effect, you may not have convex combination of individualistic treatment effect. Okay, so here, let me give you an illustration. Imagine you have these units, right? We have 4 units here. We call A, B, C, D. Okay, so the D, this D person this is getting treated, right? Okay, this is 1, 2, 3, 4, 5. There's 5 periods. This D person gets treated in the 3rd period, and the C person gets treated in the 4th period, and the B person gets treated in the 5th period. So these are treatment, right? If we are interested in ATT, we should be estimating the treatment effect over these 6 cells, right? On average over these 6 cells. That's our average treatment found treated. That's our ATT, right? So what this literature finds is that when you use a TWFE model to apply to this kind of data set, you're not getting ATT. You're not even getting convex combinations of effects over these 6 cells. Even if the effects for these 6 cells are positive, for example, the effect for this one is 1, 1, 1, 2, 2, 3, 4. These are the effects. Taking average, they should be ATT should of course be positive, right? Because every observation on top of it, it's a positive effect. But because of the weighting problem that I will explain to you, the TWFE effects estimator can actually give you a negative coefficient. That's really bad because it's basically distorting the facts, right? So you have positive facts, but you apply an estimator. This estimator does a terrible job giving you an estimate of the wrong sign. That's really bad. Okay, I'm going to explain to you why that that happens. The key intuition is that treated observations of early adopters serve as controls for treated observations of late adopters. Okay, so you still don't understand what this means. This is a key result from Goodman-Bacon. So let's say we have 3 units, A, B, C. The first unit, so they follow parallel trends. So the strict homogeneity assumption is true. The PTA, the parallel trend assumption, is valid, right? We are living in a world where parallel trend is valid. Okay, so in this case, the treatment effect for B and C are exactly the same, right? So these are the treatment effect, right? Let's say it's delta, right? So this is the treatment effect delta. These delta are exactly the same between units B and C, and over time, it's always delta. Okay, so that's an ideal case. That does not violate our previous assumptions. And then what Goodman-Bacon finds is that when you do a TWFE effects, TWFE effects is actually TWFE effects, like delta TWFE effects, is actually a convex combination of small DID and with some weights, right? It's a weighted DID. So part of this DID would be something like the purple comparing with orange, right? So if you look at this comparison, this is a small DID as well, right? So Goodman-Bacon proves that the TWFE effect will be a lot of these kind of small DID. So some of them are actually this type. These are post-treatment. This is post-treatment, right? Because this is the B gets treated as 7. This is already post-treatment. For an early adopter, B is an early adopter, but these units are serving as controls for the purple guy, for the late adopter. This C is a late adopter, right? So you are using these periods as controls for late adopter C. So in this plot, this is fine. You still can use this small DID to estimate the effect on C without bias. This is because the treatment effects are homogeneous. Let's say a different case. In this case, the PTA is still valid. The treatment, the parallel trend assumption is still valid. However, if you look at this comparison, this small DID, because the treatment effect of B is increasing over time. So it should be the case that you should be comparing this trend, right? This trend following the green one, following the dashed line, but you're actually using this steeper trend as controls for the purple guy. Then the effect for the purple guy will be underestimated because your baseline control is post-treatment, and these post-treatment effects are increasing faster than the counterfactual. So you're using wrong data as your control in the smaller DID. That caused the non-convexity issue here. Okay, so the problem is even worse when you have treatment reversal. Many of our applications in poli-sci has reversal. So when your treatment reverse back, so for example, this B gets treated period 7, and then reverse back to 11. And then this C gets treated for 2 periods and then reverse back. But in this case, if the TWFE set assumptions are correct, if the treatment effects are homogeneous and parallel trend or heterogeneity is satisfied, you have this kind of thing, this kind of figure, that's fine. But more often than not, what you find is something like this: is the parallel trends are not satisfied. You see that they're of different trend, ABC of different trends, and then you have this is anticipation effects, right? Because even before the treatment, your counterfactual is already different from the baseline where you don't have a treatment. This is a carryover effect. So when the treatment status is already gone, it's already become zero, you still have some lingering effect. Just like my cough, my COVID is gone, but I still have cough. This is a carryover effect. Okay, so and then you have parallel trend. These are the parallel trends violations, right? PTA violations. Okay, so for this type of data, you use TWFE file. We don't know what we are estimating. You have all kinds of problems. All right, so question is about whether Goodman-Bacon requires balanced panel. Yes, the Goodman-Bacon analysis requires not only a balanced panel, but also requires staggered adoption, which we'll talk about. So Goodman-Bacon actually that paper does not analyze cases with reversal, but I think the same logic would apply to such cases. Okay, so my plan today, so if some of you ask me my plan, so we want to know whether in light of this criticism of HTE and of parallel trend violation or heterogeneity violations, whether the existing studies in poli-sci, in political science, can hold in front of these criticisms, and what do they do actually in analyses, and we're going to compare the performance of different new estimators that I will talk about in the next hour. And just to preview the result, we collect 90 papers. They use panel data, with binary treatment, and then we attempt 52 papers using TWFE models. Some other papers using one-way fixed effects or other models that we don't use, the nonlinear models, so we don't replicate. And then we are able to successfully replicate 37 papers, meaning that we are able to replicate a point estimate exactly right, only one result. If one result is replicable, then we deem this paper as replicable. Excuse me. And then we conduct diagnostics based on these results. And then based on these findings, we provide recommendations to researchers in the hope that we collectively can improve practice. Okay, so this talk is based on a paper, but we not only want to summarize what's new in the literature, but we also want to apply what's new in the literature to existing papers to see whether the problems are severe and what should we do about them. And there are both good and bad news from this replication exercise. Okay, so common practice. First, most papers use to fixed effects. Most papers actually cluster standard error. That's a really good news, right? I talk about you would be asked whether you have your standard error in a talk. That's very important. That's the bare minimum you need to do if you do longitudinal analysis. About 60% of the papers have some kind of a graphic validation, like event study plot or parallel trends plot, but another 40% do not have these kind of validations. Do the results hold up? They're both good news and bad news. And the good news is that the previously mentioned HTE problem, right? So the Goodman-Bacon result is driven by the treatment effect being different over time across units as well. And we find the consequence is not very severe. It matters for a small number of papers. Most papers, it looks like it's fine. So although it is a problem that is theoretically important, empirically, it doesn't seem to be as damaging as we expected. So it's not as bad. So, but still, you want to use these kind of new estimators to avoid the HTE problem, to avoid the issue that Goodman-Bacon and other authors have pointed out. But based on the paper that we review, it doesn't seem to be an extremely bad situation. So the existing results do not get overturned because of this issue. However, we also find about 1/3 of the papers, once we apply these estimators, they are not statistically significant anymore. They lose power, and there's many of these papers were barely statistically significant. Now they don't have enough power to reject the null hypothesis. And also, there are a lot of signs of violation of the PTA, violation of the parallel trend assumption. As I said, parallel trend assumption is a implication of the strict exogeneity assumption. If you have signs of parallel trend violation, then you basically have signs of violation of strict exogeneity, which invalidates your TWFE fat approach. Okay, so after analyzing this 37 papers, we think maybe 12, 13 papers have fairly good, strong results for their treatment effect and also for the parallel trend assumption. Okay, so what's the takeaway? In case I run out of time, I don't think I will run out of time. I have 2 hours, or I have 1 more hour. These seem to be long. I have lots of things to cover, but I think the assumptions are most important thing. Once you understand what kind of problems we are tackling, the rest is actually quite easy to understand. Okay, the takeaway is that research design is very important. So you want to make sure that you are looking at a shock, maybe a policy shock, maybe something sudden. And although you're analyzing panel data, you don't require random assignment. You want this kind of shock to be sharp and sudden, and then which makes your parallel trend assumption more likely to be true. That's a first order issue, and you always want to check whether your parallel trend assumption is likely to be true. And second, this concern from the econometrics literature seems to be overblown. So a lot of discussion pointing out problems. They are real problems, and they're mathematically true. There are problems. The problems can occur, but in our review, they don't seem to be as severe as we expected. I just mentioned that. So there are about 6-7 estimators, right? So we actually develop a package for you to implement all these estimators with one press of a button. But if you actually find these estimators they should give you very similar results. If you actually find the results are very different, it means the parallel trend violation is likely to be invalid, right? So if you have a disagreement among these estimators, it's very possible that you have a violation of parallel trends. So you need to do validation, you need to make this kind of a event study plots, or dynamic treatment effects plots. I will explain. Okay, this is a roadmap. I will explain the methods. What are the new methods being proposed, and how do we apply these methods to the sample of data that we collected from mostly Harvard Dataverse and the author's website, and then report our finding of the reanalyses. Okay, so I'm gonna have another pause and see whether we have questions.
Yes, there's for those who are attending to the chat, you already post some citations, and they should be readily available in Google Scholar. And I think there's a question about Goodman-Bacon. decomposition, does it necessitate a need for a strongly balanced panel? Correct?
Yes, I answer yes. It requires a balanced panel, and it's not only strongly, it needs to be perfectly balanced. But that's not a theoretical result. That's just their software. It's easier for the theoretical results to come through. That's also what their software does. But I think the same logic would applies to other situations.
Mm-hmm. Yeah, you can click on the link I posted on the chat box, and giving the full access to the paper. I think I talked about this a couple of times, 3 times, and talking about balanced data set. All right, and do we have more follow-up questions? Well, Dr. Xu is taking a pause, and let me see. I hope we got all these questions covered. Now, I think we have a follow-up question. I'm understanding that from a lot of papers, the new HTE and estimators are used as robustness checks compared to two-way fixed effect.
I think so. I think, well, just imagine you're writing a paper as the author, right? So you want to accommodate different reviewers, right? So it takes time to reviewers and authors to educate, self-teach themselves of the new methods. And part of our goal of this paper is to summarize what's going on and then to accelerate this self-teaching process to make sure that everybody is on the same page, what this is really about. And once we know that, we can move on, right? Otherwise, like everybody's confused, nobody knows what's really going on, and then author face a trade-off, right? On the one hand, if they use one of the new estimators in the main analysis, if the reviewer doesn't understand, then they're in trouble, right? That they don't understand, they will probably not find the paper from JOE and read the paper, and that's why I think the authors would would adopt this kind of strategy. Okay, I do two fixed value, you understand two fixed value. Okay, great. And then for some reviewers or editors who really cares about this HT problem, I do robustness checks. Then I satisfy both groups of reviewers. I think that's the mentality. But in theory, I don't think that's a bad practice at all. I don't think that it has perverse consequences. But I think these days, as I will discuss, the use HT robust estimator is not you don't suffer too much cost except for some loss of power. But you don't have. Oh, my Siri, sorry, Siri is speaking. So basically, use HT robust estimator. You don't lose too much for some estimators. Okay, great. So talking about the methods, I'm going to introduce you 6 estimators. I hope that's doable. So in order to achieve this goal, which I think is ambitious because they're from fairly dense papers, so I would mostly use graphics. So for you to understand these estimators and the details, and this is an extremely simplified way to discuss these estimators. And for those who really want to do methods, you should read these papers. But for applied researchers, at least, well, if you can read our paper, that'd be great. Also, at least you need to have an intuitive understanding of what these estimators are doing. So before we do that, we first introduce the different settings to make sure we understand what's going on. So we have 3 sets of settings. One is what we call classic multi-pair DID. It is an extension of DID, right? DID is 4 cells, right? If your data is look like this one, this is like 2x2 DID, right? But we may have extension. We have more periods, more before and more after, and this is a classical multi-pair DID. Okay. Another one is very common. It's called stagger DID. Stagger means that eventually, a lot of people get treated. Maybe not everybody, but once you get treated, you never return back. It's very common, but once you adopt the policy does not reverse back because it's very high cost to reverse a policy. That's very common. Okay, so but it has some different variations of this design or this setup. So one is, in this case, there's always treated, right? A is always treated. So from the very beginning, it's treated. And you may have a case where there's no always treated. You may also have a case where everybody eventually get treated, right? So there's no pure control. We call this E person pure control. It's never treated, or you can call it never treated. And then A, C, D gets treated at different times. And also in this literature, we call units that get treated at exact same time a cohort. Like A and B is like cohort, like class 2023. So A and B gets treated at the same time 3. So they're from one cohort. C is a cohort in itself. D is a cohort in itself. Okay, that will be used for later. Okay, so there's a more general setting, which is that there's treatment reversal. The 0 becomes 1 and the 1 becomes 0. And yeah, it's all over the place. It's hard to determine the pattern. So that's what we call the general setting. In general, we allow a reversal. If we allow reversal, it's what we call a general setting. Okay, so here I put down the two fixed fact specification here, just as before. And then we also have a dynamic specification. Dynamic specification is as follows. The two fixed effects, these are fixed effects, right? These are the same. These are covariates. All right, so these are error term, just forget about them. So what are these? These K. K's are the relative time. K equals to 1. So KIT equals to 1 means that it's the first period after the treatment starts. At KIT equals to 2 means that the second period after treatment starts, right? So basically, you're dumbing out different time periods relative to the start of the treatment. So in this plot, this will be 1, 2, 3, 4. This will be 0, 0, minus 1, minus 1, right? So again, this will be 1, this will be 0, minus 1, so on and so forth. That's what this K is about. You estimate this model in a dynamic fashion, then you would have this kind of this set of coefficients. So for example, delta minus 4, delta minus 3, and then delta minus 1. Maybe you omit delta 0, and then you have a delta 1, delta 2. Then you plot, these are estimated. Then you plot them, then it gives you an event study plot, right? Or dynamic treatment effects plot. And then you also have a absorbing status. So after 5 periods, I lump all the data together. These are 5 years after treatment. I don't differentiate them because I don't have enough data. Okay, and then this is what we call the long-term effect. This is actually from the BJS paper recently published in RES. Okay, so one thing that keep in mind is Sun and Abraham, they show that even with this relaxed assumption, this is more flexible modeling assumption, you still may have these delta to be biased, again, biased toward ATE. This is not a good estimate for ATE if you have heterogeneous treatment effect. So when you have heterogeneous treatment effect, this is better than this one. This dynamic specification is better than static one, but it does not guarantee this delta is unbiased. You still may have a problem. Okay, so I want to introduce this just to serve as a benchmark. Then I'm going to introduce the 6 new estimators. The first estimator, sorry, before we do that, we want to emphasize that these estimators all they do is to relax the heterogeneous treatment effect assumption. Right? Previously, we assume delta IT equals delta. That's assumption, right? Everybody has exact same over I and T have the exact same delta. Now, under these estimators, they allow delta IT to be arbitrarily different. It can be anything. But these estimators, they all require parallel trend assumption to be true. Right? You need to require PTA to be true. And then we put them into 2 categories. The first category is what we call the DID extension. In DID extension, they are basically estimating a lot of 2x2 DID. And once they have these estimates for 2x2 DID, they reassemble them and to estimate cohort average treatment effect and average treatment effect. Some estimators are only applicable to staggered setting. Treatment from 0 to 1 never reverse back. Others allows general, so they have allows reversal. This does not allow reversal. Okay, then a different type of methods is called imputation methods. It allows reversal as well. It also estimates ATT. Okay, so give you a graphic representation of these estimators. So here I show you 4, but actually there are 2 more that are basically represented by these graphs. So you don't need to understand what they mean. So I just want to give you a graphical understanding of what we want to introduce using this type of illustrations. We have DID extensions applied to stagger setting. I'm going to introduce you 2 different estimators, and then we have DID extensions to apply to general setting, but this is basically a matching method. Matching methods will be here. They are DID extensions, but they can accommodate reversal, and then the imputation methods also can accommodate reversal. Okay, then I'm going to start discussing each of them. So the first one, so once we finish the first one, everything becomes very straightforward. The first one is what researchers call interaction weighted. It's called interaction weighted because you can literally estimate this, get this estimate in data using interaction regressions, and then you get the coefficient and then reweight the coefficient. But I'm going to explain to you using graphics. So for this estimator, it requires the data to be staggered adoption, right? So it does not allow reversal. Okay, so this estimator only is useful when you have staggered data. So eventually, well, it's okay that you don't have treatment, but it actually requires there is a pure control. So this is what we call the pure control or never treated group. Pure control. But it cannot reverse back to 0. Okay, the treatment. So what it does is always to compare to, for any cohort AB, cohort C, cohort D, always compare to cohort E, which is never treated. Okay, here, although it looks like there's only 5 units, here actually E maybe represents many units that are never treated. Okay, so what it does is to reduce the problem or simplify the problem back to multi-period DID. So basically, it's estimated the cohort average treatment effect by cohort. So when you estimate effects for A and B, for cohort AB, you are ignoring information from CD, and then you are just estimating the effect for these guys, right? And this is very easy because it's it's classic DID. You can apply difference in difference. You can apply TWFE effect. TWFE effect at that time is numerically equivalent to difference in difference. So that's fine. So what you do is like why it's DID extension, a 2x2 DIC extension. You basically use these 6 cells. This is a 2x2 DID, right? 0, 0, 1, 0, 0. You get treatment effect for these 2 units for cohort at this time, and then you move, and then again you have 2x2 DID. Again you have 2x2 DID. So all these 4 periods you use 2x2 DID to get the average treatment effect on the treated to get ATT. Okay, once you have that, you move on to a different cohort C, and then you do 2x2 DID, 2x2 DID again. Okay, and then for D it's the same. So once you have that, you have the cohort average treatment effect, then you weight the cohort based on the sampling weight. So for example, this cohort will weight twice as much as C because it has 2 units than 1 unit instead of 1 unit. Then you basically reweight A, B, C, D based on their sampling weights. That's interaction weighted. Okay, so here, why this estimator is HT robust? Because it never used, okay, so remember HT problem only matters when you use early adopters as later adopters control, right? So these A, B are early adopters. These C and D, relatively speaking, they are late adopters. But when you estimate the effect on C, you never use information from AB. You only use information from E, right? When you estimate the treatment effect on D, you never use information from ABC. You only use information from D and E. That's why you avoid using the bad comparison from early adopters post-treatment data. That's how it avoids the Goodman-Bacon problem. Okay, then a very related method is proposed by Callaway and Santana, 2021. So that paper has a lot important and interesting thing inside the paper, but from estimator, so including like doubly robust estimator when you have covariates. But what I think is interesting in terms of the construction of estimator is comparing with Sun and Abraham. It also proposed using not yet treated to estimate ATT in a 2x2 DID setting. So for example, if I want to estimate the treatment effect ATT on cohort C, right? So Sun and Abraham would only use E because Sun and Abraham always compare to the never treated group, to E, in this case to E. But for Callaway Santana, what they say is, okay, so when I'm actually estimating the effect for C, so I should also use information from D, right? Because D is not affected by treatment yet, assuming there's no anticipation effects. But if there's no anticipation effects, I should use more data to estimate ATT for this guy, then I have a more efficient estimator. So one question in the comment section says Sun and Abraham doesn't use pre-periods. Actually, what Sun and Abraham does is always compare to the 1 period right before the treatment starts. For a different cohort, the reference point will be different. And then all the pre-periods will also be compared. They also do a 2x2 DID using pre-periods. These are used to gauge whether the parallel trend assumption is likely to hold for the event study plot. But for estimating ATT, my understanding is that the original paper do not use all the pre-periods for estimation. They only use 1 period right before in estimation. Okay, so sorry. Okay, let me, one of you asked me about the package, so I will show you the package in the end of the talk. Okay, so let me finish this talk first. Okay, I talk about Sun and Abraham and Callaway Santana. I hope you get the intuition. So they are, Sun and Abraham always compare the treated with the never treated. Callaway Santana, they compare not only to never treated, but also not yet treated. Okay, that's the difference. Okay, then the second, I don't know whether you still remember, the second set of estimators are the matching estimators. They are still using 2x2 as building blocks, 2x2 DID as building blocks, but now they can accommodate treatment reversal. The cost is that you actually throw away a lot of data. You chop data into pieces in the matching process. For example, Deschamps-Martin, the Fourier, two French econometricians. So what they propose is to there are no cohorts, different from the Sun Abraham Callaway Santana. They only look at switchers, right? They're only focusing on from 0 to 1, the immediate effect from 0 to 1. Then they match these switches from what they call a stable group, whose treatment status do not change during the same period. Okay, let's focus on these two units. Right, these are from 0 to 1, 0 to 1. So let's say I'm interested in their immediate effect 1 period after treatment started. And then what they do is, oh, this is the treatment group, right? This is from 0 to 1. They switch from 0 to 1. And then they try to find a stable control group or stable group in their notation. And these units will serve as stable group. Then they use this set of units as 2x2 DID, right? You estimate 2x2 DID. If the parallel trend assumption is valid, this will give you an unbiased estimate for the ATT for first period after getting treated for these two units. Okay, that's very basic, very like straightforward idea. Of course, you can look at 0 to 1. You can also look at 1 to 0. Okay, so what's downside here? It's quite obvious actually. If I were in a class, I would ask students, The downside is that you basically break down the panel structure, and you're not looking at long-term effects. You're only looking at short-term instant effects, right? So many policies, they don't have short-term effects, or short-term effects does not represent the long-term effectiveness of a policy. Then you're in trouble. And also, it's like less likely to be very efficient, right? Because you throw away a lot of data. Okay, so almost similar times, right? But I think they write the papers simultaneously by Kosuke, Song, and Eric. But all of them are my friends and teacher. They have a similar idea, but they are slightly more more general. Instead of saying that I only look at switches from 0 to 1 for one period, they're saying we can actually look for more into the future and more back to the past. Okay, so they say, okay, I'm not only looking at one period right before, I'm looking at 2 periods before. I can also look at okay, so for this is the guy we're interested in. So this is 0, 0, 1, right? Okay, so if I'm interested in this guy's effects, the effects on this guy, I can use A, C, and E as my control, right? Because A, C, and E both have 2 periods that are not treated before this period, before the 3rd period. But I cannot use D because D is being contaminated by the treatment. So I can only use ACE as my control. So if you use ABCE, that's a 2x2 DID. That's a 2x3 DID, right? A multi-period DID. That's fine, but D cannot be used. They also say, okay, so use this data is 2x. This data is 2x2 DID. But they also say I can look into the future, right, for a longer period of time because one period is too short. And then they say, okay, if I commit to 2 periods before, 2 periods after, that's doable. But the problem is that A no longer can be your control, right? Because A is already treated. So A is not a fair control to B anymore. You can only use C and E as your control. But again, once you have the match set, this becomes a 2x2 DID. You can still estimate the effect using a 2x2 DID. Okay, so but as you can see, these two methods are closely related. I see the Chasman TWFE paper as a special case of panel match, and panel match also can refine on other covariates. Okay, so I see DID as a weighted sum for panel match. Okay, the last group of methods is what we call imputation methods. So we wrote a paper in AJPS, and Boryszak and the co-authors. So this person is actually a Stanford scholar, a friend of mine. So actually, we don't know we are working on similar things, but this paper finally is published in RES. Both paper, they have the same estimator, but we have different directions. So we also incorporate factor models, and they show the efficiency properties, and they also show the under-identification properties when you have anticipation effects. But anyway, the estimator is the same. So the idea is also extremely simple. So let's say we have this type of data, and what we suggest is that we don't use the treatment data. We treated data. We pretend they're missing, right? Causal inference is a missing data problem. So we fit model for Y0 only, for the non-treated data only, right? So for observation under control conditions only. And then what we call a TWFE counterfactual estimator. And then we impute Y0 for the missing periods, for those periods that are under treatment condition, are actually under treatment, they are not really missing, but we treat them as missing and then impute counterfactual. And then once we impute it counterfactual, we take a difference between the two, and then we average over delta IT. Or delta IT, for each observation, you have a delta IT, then you average over delta IT. Okay, as you can see, you don't have a Goodman-Bacon issue of bad comparison, because we never use post-treatment data to estimate counterfactual, to estimate to serve as controls for treated units because we treat them as missing. And the BJS paper proves that this is the most efficient estimator if you have homoscedastic error terms. That's not surprising because if you have homoscedastic errors, and this estimator will use information most efficiently because it's an ORS, right? Essentially, it's an ORS with additive fixed effects. Okay, so just to summarize, if we have staggered adoption, all these estimators can be used, right? So these they will construct the estimator differently. Interactive weighted or and staggered DID I haven't discussed. They would use never treated only, and CSDID would also use not yet treated, and DID multiple will only look at the switchers from 0 to 1, and panel match will can look longer, and the imputation methods are our factors for fixed effect counterfactual. They used all data for counterfactual prediction and then average over the estimated individual treatment effects. However, if you have reversal, right? If you have reversal, these two are not applicable, right? These two only applies to staggered. Okay, so to summarize here, staggered, general, different estimators, they have basically same assumption. The notations are a little bit different, definition a little bit different, but they all rely on parallel trends. And as I said, parallel trend is a special case of strict homogeneity. If you have strict homogeneity, all these methods, if the settings are suitable, will give you unbiased estimate for the ATT. Okay, so just to pause a little bit here, looking at this table, so you kind of know if you have large enough sample, these other estimators, they should agree, right? They should agree because their estimates are very similar. So CATT, you're looking at the cohort average treatment effect, but you can also weight the cohort average treatment effect to estimate ATT. So basically, all of them are focusing on ATT, and if the sample size are large enough, they should give you the same answer, right? That's basically they're converging to the same quantity. But in reality, if there are significant differences among these estimators, it means what? It means the parallel trend assumption is likely to be wrong because these estimators are different in the way they weight the control units, right? So obvious example is between interaction weighted and CSDID. IW do not use not yet treated. CS use not yet treated. Counterfactual use everybody. So the weights they give to the control observation are different. All right. So and when you have parallel trends to be invalid, these different differential weights, different controls, will result in differential estimates between these estimators. But if your strict identity is correct and it's in a staggered setting, they should converge the same quantity. Okay, I hope that's clear. All right, so next half an hour, I can pause a little bit to see if there's any questions. I've answered the questions I've seen, but if you have more, you can ask. Carl, I've answered those questions already.
All right, if you still have more questions or follow-up questions, please do not hesitate to type it in the chat box. Now there's one here. All estimators are applicable under staggered adoption?
Yes. Yes, correct.
Mm-hmm.
But the first two are not applicable for reversal, with reversal. Mm-hmm. Okay, great. Okay, let's the more exciting results on how the existing paper do with this new estimator. We basically apply everything to every paper that's possible that can apply this method and see what the results are. Okay, so I'm going to be a little bit faster on the case selection, although I think we have time. So we start from 90 papers that are using panel data, and then 52 use TWFE fixed effects, and then some papers, about 1/5, have incomplete data. Some of data cannot be found. So that dropped, and some of these papers have errors. So we end up being able to replicate one main result. We only replicate one main result, and the result usually is the strongest result in the paper, and also the author's preferred result or preferred specification. So we are able to replicate about 71% of all the 52 papers. Okay, so what the common practice I've said, I've previewed earlier, most papers use this setting. Every paper use TWFE effects. Excuse me. But about 60% have reversal, so it's like the general setting. One third, close to one third have staggered, and some have staggered DID. Maybe two papers or three papers have 2x2 DID. Okay, so cluster error. Most papers use cluster error, and some of these papers also look at additional specifications like unit-specific linear time trend or add lag-dependent variables. And some papers have event study plot, but about 40% has no data visualization. Okay, so what do we do? So we first, of course, we have to read the paper, and we understand the context, we understand the setting, we understand the data structure, and then we plot the raw data, we record the key information from the papers. And then we replicate, we choose one result that is the strongest and the most preferred by the authors. And then we use the original variance estimator or cluster bootstrap procedures. We use the original variance estimator, but we also use the cluster bootstrap procedure that most papers do not use. This is a more conservative method to get standard errors in a panel setting. Then we apply these methods, IW6 DID panel match. Because the IDM is a special case of panel match, we only use panel match. We use imputation. Everything is applied for stagger case, but for the general case, we only use panel matches and imputation. Of course, we also apply TWFE effects. And then we conduct diagnostic tests based on our imputation methods because we know the software better. Okay, so to give you an example how we do this, so this is one example. The others are looking at the effect of co-ethnic mobilization in the U.S. context. It's basically asking whether a minority candidate will able to mobilize more donations from the co-ethnics. For example, there were Taiwanese American running for congressional elections in the United States, whether Asian community will donate more in that race, right? That's very straightforward. They also look at the Black candidates and Latino candidates, Asian candidates, Black candidates. So in this plot, we show the Asian candidates. It's very straightforward, right? So if you have an Asian candidate, Asians are more likely to donate. And okay, so the outcome is share of co-ethnic donations. Sample size 489. And this, for those who are familiar with U.S. politics, the congressional districts are 435. And the additional number is because of redistricting. And then there's 17 congressional races, the congressional cycles. Every 2 years there's a cycle, and about 7,000 observations. And this darker blue are when an Asian candidate is running for in that election year. And we can apply different estimators, right? Because this is a general setting. TWFE effects and the imputation factors, imputation methods, and then panel match. They show very similar results. Then we compare the estimates. Panel match is slightly smaller, but they're essentially the same. Right? You cannot tell apart statistically from them. The two colors represent cluster error and the bootstrap standard error. They're also very similar because of a large sample size. Okay, so for diagnostic tests, we use F-test that we developed for pre-trained. We also used a equivalence test. The equivalence test is basically saying we're flipping the null hypothesis. If we reject, it means that we have a strong piece of evidence that the pre-trained are within a narrow bound, right? So in the original F-test, if we reject, it means that they're different. If you reject that they're all zero. If you reject, it's a bad thing. in equivalence test, if you reject, that's a good thing. Okay, that's something, because in this case, if you don't have enough power, you cannot reject, right? But you cannot reject does not mean it's good. Basically, it could mean simply you don't have power. With the equivalence test, when you have more data, you're more likely, if the assumption is true, you're more likely to reject, which is a good thing. Okay, so we conduct this test, and we also conduct a placebo test where we hide a few periods before the treatment starts and to see whether the counterfactual is actually, whether there's any time variant confounding or whether there's any anticipation effects. In this case, there's not much. So 2 years before an Asian candidate run, Asians do not donate more compared with the benchmark. And that's what this figure tells. Okay, so we also look at carryover effects. This is 3 years after a Asian candidate run. What does this mean? This means basically if last cycle, 2 years ago, an Asian candidate ran, but this election cycle, there are no Asian candidates, so Asians' donation returned back to the normal level, right? So there's no carryover. Previous 2 years, the mobilization effect is already gone because there are no Asian candidates. That's quite straightforward. But this is actually kind of rare because in most policies, they have carryover effects, except for this one. This one, because it's election, carryover effects does not exist. That's not surprising. Okay, if you reject, it means there's evidence of carryover. If these are different from 0, it means there are carryover effects from Asian candidates. But in this case, we don't have any evidence of carryover effects from Asian candidates. Okay, now we apply this procedure to every paper that we are able to successfully replicate it. And we find a few problems. One is missing data. One is signs of PT violations. So we have some clue, some indication that the strict zonality assumption may not hold. And we also find a key question we want to answer is whether the HTE or the weighting problem that so many authors have written about actually matters. We find that they matter marginally. Most of the estimates are similar to twist fixed effects, and most of the estimates tend to agree with each other, but they have some power issue. We also show some results for the carryover effects. Okay, so missing data is very bad. This is actually because when the authors were writing this paper, there are no tools to plot the treatment status over time. So that's why we actually develop a tool called panel view. In both panel view, VIEW. This V is capitalized in R and also in Stata as well. In Stata, it's not capitalized. Everything it's lowercase. This is Stata. So we develop two packages for you to just visualize your treatment status. And the treatment status can be non-binary as well. So there has been a lot of downloading, which makes me happy because I think this should be a standard practice. We should know where our variation comes from, how many missing data there are. If you look at missing data, something like this, you should be very worried, right? Because it's hard to say what you are comparing. Okay, and second, PTA violations. There's one paper, the author looks at this particular problem, whether lawsuits against city on rezoning increase diversity of city dwellers. The finding is negative, right? But if you look at a study plot, this is from the imputation methods. You see a strong trend leading toward the start of the treatment and downward trend. And then if you, of course, the F test rejects, which is not good. And if you do a placebo test, it rejects, which is not good. If you data use interpolated data, if you remove the interpolated data, original raw data, you see the same thing. If you add a unit specific linear time trend, it basically kills all the effect. Okay, so that's one case case that is clearly you have signs of violation of parallel trends, and once you account for what potentially causes or at least adjusts for differential trends, the effect no longer exists. So that if you see something like this, you should be really worried whether this this negative and the large statistical coefficient effect coefficient are pointing to something real. So it's highly unlikely in this case. Okay, in summary, 24%, which is not a lot, rejects the F-test, the knowing the F-test. This is a bad thing. 17% rejects the null. And the null numbers are small because the power issue, right? We don't have much power. But if you flip the null, use the equivalence test, actually half do not reject the equivalence test. This is actually bad. We want to reject in the equivalence test. So most papers cannot reject because power. So you see all kinds of violations like this. But a lot of papers looking pretty good. You don't reject with F. You don't reject with placebo, but a lot of them is actually you have power issues. Okay, the next question is, do HT change substantive findings? I've told you that it does not usually. These are the original TWFE effects estimates. These are estimates from our fact package from the counterfactual estimators. They're normalized using the same standard error estimates because the denominator are the same. So the only difference is because of the estimator has changed. The point estimate has changed. You see, most of them are on the 45-degree line, close to the 45-degree line. There's some have big change. The red ones are becoming statistically insignificant, but most of them they follow the 45-degree line, and they don't flip signs. Right? There's no such things like, oh, the effects should be positive, but TWFE effect has a negative coefficient. That never happens with this case, with this the imputation methods. Okay, so if you plot the ratio between imputation and TWFE effects, it does it does have a spread, right? Some overestimation, some underestimation, but the mean and the median are very close to 1, and some once you use the imputation methods become statistically insignificant. Okay, so you don't have systematic over and underestimate or underestimation, but it is a problem that you should pay attention to. Okay, so these are it's about 21% of the paper. Once you use the imputation methods, the coefficient is reduced by 20% or more. I don't know whether that's a big or small number. I think it's reasonable. And there's only one study that the effect is reduced by over 50%. And the mean and median are about 1, so there's no systematic over or underestimation. So once you applied this estimator, the imputation estimator, results become statistically insufficient for 1/3 of the studies. Okay, so you can subjectively argue this is a bad or good situation. I think it's overall from a Bayesian updating point of view, a good result, because previously we saw all the results are going to be in trouble, but actually they only matter marginally. Okay, so for the staggered cases, for 7 papers that have staggered adoption, so we actually can apply all these different estimators. They do vary, right? Some are really close, but they do vary. And only in one case the sign flips, right? In this case, sign flips actually, but other cases they're not flipping. In general they agree, but there are a few cases there are substantive differences, and usually those cases are when you have a lot of uncertainty. The treatment fact is barely statistically significant. The estimators, they tend to agree, although underpowered very often. As I said, they should agree, right? The shape should agree. And there are exceptions. There's very interesting exception that I want to talk about by 2 friends of mine. So we are actually together writing a paper with these 2 authors because we find something really interesting I want to explain to you. And we decide with the original authors, I reach out to them and very gracious, and then we want to write a paper together. So basically, they study whether titling can increase property tax revenue, okay, in a Brazilian context. But you see a vast disagreement among different estimators. You use different estimators. Some are positive, some are negative. In the paper, the original paper, the reported is positive. But if you remove always treated, it becomes negative. Reported is TWFE fixed value as 2, but this TWFE fixed value is removing the always treated because all these new estimators will remove always treated, and they are disagreeing with each other too. Okay, so what's happening? So in the original paper, for the event study plot, it's a positive effect. Okay, that's the original paper based on a subsample. Okay, what's happening? What's happening is, again, if you draw the treatment status, it's a staggered adoption, but the never treatment group is very small. The never treated group is extremely small, and they're quite different. So here is a cohort outcome trajectory. If you look at the never treatment group, this has a steeper trend, right? This trend is much more steeper than those observations that are treated. And essentially, if a estimator that puts a lot of weights on the never treated, you will have a very negative estimate. If an estimator basically discard or put very little weights on the never treated, and you will see a small positive effects. That's what's really going on. And if you look at Goodman-Bacon estimates, and both red and purple, they are acceptable by Goodman-Bacon. They are good comparison. The red ones are comparing the post-treatment for the late adopters against the sorry, I was wrong. They're comparing the treatment versus of the early adopters against the control of the late adopters. That's the red one, that they are positive. Another comparison is comparing treated versus control, never treated. That's the purple. And because this purple line is so steep and different from the rest, you have negative estimates. All right, this is basically because this never treated group is very different from the rest of the observations. So in their subsample, you actually see consistent estimate. This is actually because in the subsample analysis, they actually trim the data to remove units that look dislike the treatment groups. Then everything becomes like very, very homogeneous, right? They almost look exactly the same. And that gives you the consistency result, not statistically consistent, but agreement among these estimators, because now the PTA violation problem has been addressed after you trim the data. Okay, that's what we find. If you look at event study plots, if you use the full sample where you potentially have PTA violation, you have very kind of different estimates. But once you have subsample, they all look very similar, although the effect size is kind of small. Okay, carryover effects, as I said earlier, for the Asian mobilization, co-ethnic mobilization, there's no carryover, but there are other papers that have carryover, right? For example, this paper. There are a couple of papers, most papers actually have reversal, you have carryover effects. So that's something to be checked. You actually can deal with carryover. You simply omit a few periods where you have carryover. That's not a huge issue. Okay, that's a summary of what we find. We find missing data, big problem. We find a lot of violation of parallel trend assumption using the imputation estimator. We find that HT robust estimator do change results, but only marginally. There's no systematic overall underestimation. We find there are signs of carryover effects in a lot of cases, something you want to look into as well. Then we can improve practice based on these findings. Okay, so overall, parallel trend violations remains a big concern. A lot of, basically, we don't have enough information to say that the pre-trend is great because of power issue. And then imputation, so HT robust estimator, they do change results through reduced power, but not because they systematically under or overestimate the treatment effect. And about 30% of the studies in question because of power issue, right, or because of you don't have enough information to confirm that your pre-trend looks good. And so carryover effects for about 1/3 of the paper, so that's the issue. So overall, you'll find like solid evidence for about 1/3 or 32%, 40% of the studies, depending on which criteria you use. If you use a more stringent criteria like equivalence test, it's like 30%. If you use less stringent tests like F-test, you have 40%. Overall, a lot of studies have two issues. One, underpowered when you have HT robust estimator. Second, I think a first order issue, you have violations or signs of violations of the PTA or parallel trend assumption. So for the rest, we cannot say conclusively. Okay, 10 minutes. But to conclude, these are the conclusions in the paper. You can read our paper. I'll send you the link to the paper and also to the appendix, which is like 250 pages long, because we have the markdown files, the reanalysis of every single paper in the markdown file. But in the paper, we provide you with some recommendations. These are too many words that should never be in a slide. But to summarize, we should always focus on design, right? We should like take advantage of some kind of policy shocks to identify the treatment effect of a policy. Design is very important, both research-wise and both statistically in terms of causal inference. You also need to understand your data really, really well. You want to look at how your treatment status is distributed and what kind of setting you're in, right? A lot of researchers, they don't look at their data enough. They just log into state-RR and run regressions right away and export tables. That's not the right way to go. You should at least understand your data, visualize your data first. And then sometimes you do want to trim your data to make sure that the treat and control are comparable. Although parallel trend assumption does not require random assignment, you do want them to be more comparable. Okay, I think that's a key message. Using HT robust estimate is not a bad idea. You may lose some efficiency, but you can prevent bad things from happening, right? Sometimes the TWFE is misleading. It can be misleading as much as 50% in an extreme case. In some other cases, 80%. So 20% misleading. So you do want to use some of these estimators, and we provide tools for you to implement these estimators. When you choose estimators, right, it depends on what kind of comparison you want to make. If you really just want to compare to never treated, which is fine, which is very transparent, you use Sun and Abraham. And then the first order issue is what kind of setting you're in. If you have reversal, then you cannot use some of these estimators. If you don't have reversal, then you can use these estimators. But you want to ask yourself what kind of comparison you want to make. And I'm a big proponent for imputation because it's very straightforward, and also because we make the software relatively easy to use. If you see disagreement of these estimators, usually it's a sign of your design issue. If your design is problematic, especially that you may have parallel trend violations. Okay, we provide tools panel view in RS data, provide facts in RS data on my website, which is imputation method. We have this URL for panel tools, which implements all different estimators, all 6 different estimators. And this is a screenshot. You can click and learn how to implement these estimators. Of course, this is not only done by me and my students. This is built upon the original author's contribution. We are basically writing a wrapper, putting them together, giving them the same visualization, right? So then you run this, you can have the same event study plots, and you can compare them. You can maybe potentially find where the problem comes from. Okay, that's all I have, and I can stay here and answer questions. Okay, I see 2 questions here. So last one, in the new estimator effect power, we are all the papers in the panel strongly balanced. I don't understand this question, sorry. So the last question I don't understand. In summary, checking for pre-trends requires 3 methods. Yeah, well, in our paper, yes, but there are other methods. Well, I don't want to give you the impression that there's only this method. Jonathan Ross also proposed different methods. So in our paper, we propose F-test and equivalence test, and also placebo test. But carryover effect is not for pre-trend, it's for whether you have lasting effects. Okay, and then I'm looking at, does this mean that we should include data in our model that goes completely untreated? That's the imputation method. Imputation methods only use untreated data to impute missing counterfactual, and then use the treated data to take a difference. Then you have the ATT estimate. That's all I have. Yeah. If you have more questions, feel free to.
Yeah, Professor Zhu, I was wondering if I could just ask you directly, if that's all right.
Yes, please.
Sure, go ahead.
Yeah. So I wanted to talk about actually the pre-trends and the parallel trends violation. So for clarifications to preface this, so if pre-trends do not exist, that means parallel trends holds.
No. Parallel trend assumption, sorry, I'm having a cough candy.
No worries.
Parallel trend assumption is not directly testable because it involves counterfactual. Right? Because it involves counterfactual, you cannot use data to directly test parallel trend assumption. However, if by looking at the pre-trend, you see there's a pre-trend. So pre-trend, let's say the I to I apostrophe, the parallel trend between these two pairs, it's already not parallel. It's not already invalid. It's highly likely that such biases will be persistent in the post-treatment period. That's the logic. We're not directly testing PTA, but these tests are indicative of how likely the parallel trend will last, will be valid before and the post-treatment periods.
So given the recent literature that's been going around, how should we still prove parallel trends? Because before it was a matter of visual interpretation, right? Through an event study plot and just identifying whether or not.
We still want to do event study plot. There's nothing has been changed. We just want to do better event study plot. So all the event study plot here, they are using a HT robust estimator. So they do not suffer from the HT problem. They may suffer from a violation of strict exogeneity. You can still do parallel. You can still check pre-trends. You can still do event study. And what we did with this tutorial, let me find it, is to show you different ways of conduct parallel trends. Sorry, event study plot. Let me show you here. So this is so all these methods they can all produce a event study plot. So you can use this. This is two fixed effects. You have an event study plot. You may argue this is invalid, maybe problematic because of Sun Abraham's paper, but you can use the robust HT robust estimator to have event study plot. This is an event study plot based on IW. CSDID have an event study plot. So every method we implemented event study plot.
Right. I guess my question is, so I've used a bunch of these plots. I'm working on a paper right now, currently implementing all of them. My question is, I guess, is how if parallel trends are violated, is there a way to be able to prove? You said that's a problem with the design if the robustness estimators do not match up, right?
Yes. So okay, so your question is, what do we do, right?
Yeah. What is the next steps? What exactly do we do to solve it?
So I taught a panel causal inference methods short course. The next steps are, well, apart from collecting better data, do better design, what you can do is to do some adjustment. There are three approaches. One is a modeling approach. You can use the factor model approach or matrix completion. The second is the weighting approach, where you basically try to reweight the control to make the control more like the treated. So one special case, very prominent case, is synthetic control. Synthetic control is to adjust the control units based on past outcome and pretreatment variables to make the trends more alike. And then the third approach is a hybrid approach where the outcome model and weighting are combined, like SDID, synthetic difference in difference, or augmented synthetic control. These are to adjust weights for the controls to make parallel trends more likely to hold. Yes, there are, but it's another 2 or 4 hours conversation.
Right. And then my last question is, it's regarding, I guess, functional form when it comes to parallel trends. I know there was a paper done by Roth and Santana that
Jonathan Roth.
discusses this.
Yeah.
Yeah. And so I was wondering if you had some insight on exactly if there would be any sort of, change, or what would be expected of parallel trends in terms of sensitivity and functional form.
Well, I think our paper in AER, I think it's in, I don't remember, I don't exactly, sorry, but so the paper is about, so when difference in difference is scale independent, the result is that to provide a sufficient condition for the result, which basically requires random assignment plus a stable group. But I think it's very informative too, because it means if you want to get scale independence, you want to get very close to a experimental setting. I think it boils down to, so our goal, right? So just step back a little bit. Our goal is the reason why we use models like TWFE effects has a historical reason, but from today's perspective, is not because we believe this outcome model so much. Is actually we want to account for unobserved confounding, right? But to account for unobserved confounding, the unobserved confounding is exhibiting itself in pretreatment data. And then TWFE effect is to say, okay, I can use the pretreatment mean to serve as a bridge function to represent unobserved confounding. I can also use my neighbors or those pure control group to capture the common trend difference. And then you can ask yourself whether you believe these two approaches to account for unobserved confounding. I believe in the future there will be a spectrum of methods that relax the functional form assumption. Maybe if you treat the common trends as estimating different time effects, this is not that crucial. The more crucial thing is how you control for individual heterogeneity in a more non-parametric way. So basically, the demeaning gives you a way to save dimensionality. Right? It's a very easy way to reduce dimensionality. You basically what you're saying is that, okay, I demean, I subtract the mean of all my pretreatment outcome, then I believe this is the right way to deconfound. If your belief is right, then it's a very efficient estimator, but it can be a wrong belief. Then maybe the synthetic control is to say, okay, so I don't want to just demean, I want to customize the weight to account for such confounding. I think we're gradually moving toward that direction. But there will be a spectrum. The end of the spectrum is that you don't believe in additive fixed effects at all. You only believe in like ignorability, believing like the non-parametric version of AIPW. So you use all the pretreatment data as covariates and then non-parametrically estimate. But when you have a long history, it will be very data hungry because dimensionality is so high. Sorry, yeah, so a lot of you maybe it's a digression.
Cool. And then just one last question. It's just, I guess, in regards again to pre-trends,
Okay.
right? So
Okay, one last question because I want to pass time to Taiwan side too. All right.
Okay, sorry
Please
about
go
that.
ahead.
So this last question is just again about pre-trends. So suppose someone is running a staggered design adoption model. What are the pre-trend checks that you would, I guess, consider, or you would recommend to consider?
Well, well, I think they should give you pretty much if the result is very sensitive to the type of test you do, that's problematic. But I like our F test. The only problem with F test is that it can be when you have a lot of data, the data has some noises. It's very easy to reject. That's why we have this equivalence test. The problem with the equivalence test is that you have to commit to a threshold. But the choice of the threshold is an art, right? So you can benchmark against a hypothetical, what you believe to be reasonable ATT, and use that to conduct the equivalence test. The other authors have also introduced similar tests, but I don't like what I like about our approach as a promotion is that we use all the pretreatment period as reference period, but most of the other pre-trained tests use one period, which is less powerful. So statistically, is less efficient.
Thank you so much.
Of course, thank you.
May I pass on to Dr. Pan? Professor Pan, do you have any questions from your side or from students in your classroom, or feel free to pose a question. Can you unmute yourself?
You're muted. Yeah.
Yeah. Good.
I think you're muted in the system.
It's still muted.
Here, can you hear me now?
Yes.
Oh, okay. All right, it was muted. So yeah, I want to say thank you, and because this time is up, but still have to say thank you for sharing this the insights. We understand that today's topic is by default, and the technical sense is about how to fix the problems in data analysis. But some of our audience are not particularly familiar with all econometrics basics. So could you take down a few nuts and give us a few more like real life policy examples or research contexts from the studies that you replicated, so to illustrate how a research should be well designed in the first place, because at the end of your presentation you said design. So design was the first question or concerns about all these data analysis. So just if possible, just share a few
Yeah, I think
real life context.
So what we mean by design in causal inference has a special meaning, which is you want to understand your assignment mechanism very well. So a classic example is return to education, right? So from labor economics, where causal inference is introduced to social sciences in the first place, like by Josh Angress, a bunch of people, Carl Kruger. If you don't understand how and why people go to elite colleges, it's a classical American U.S. labor economics question. However, you control for the potential confounders, family background, education, wealth, you cannot estimate the return to education very well. But later, what they find is that if you are getting very close to the assignment mechanisms, either you randomly assign or it's experiment, or you can collect information on for example, the selection mechanism. If it's a scholarship based, you have a score, like the RD idea, or you actually have the information of what kind of school the students are applying to and what kind of admission offers they get. And once you control for these, and then the rest selection is more minimum, and then they find you can actually estimate the effect of education to return to education much better. But what I mean by design is if you want to achieve causal inference in a credible way, you instead of running kitchen sink regression, putting as many variables as possible on the right-hand side, you want to have a deep understanding of why some people choose to adopt this treatment, why some people or units choose not to adopt this treatment, and then you're getting closer to the design. So in the panel setting, it's why this state or this locality adopts a policy or elects a certain person, why the other locality do not.
Okay, thank you. Carl, do you have more questions on your side?
I do have a lot. I know time is running up, running out, and so maybe I can ask one general question, and So I think as Dr. Xu teaches data science, and we are talking about two cultures, and one is big database, the other one is a small database, and like Brian talking about the data model versus the algorithmic model, and so one thing I think it is really important that you brought up is bring back to the design and bring things back to the drawing table. Get to know that some co-founders and you want to think through about it instead of pulling all the variables and which is what machine learning is doing, and then try to come up with a prediction model. And I think this is something we can think more generally in future, our research design, and more going back to the small data, which is we still very focused on a design and on the hypothesis we must think about, versus the abundance of the data, abundance of predictors or features you want to pull into the model. Then you use lasso or use methods like all these selections and make a good model to predict. So there's still a long way to go in order to bridge the two. And particularly when you talk about I think you also highlighted the power, when that will be a concern to particular and which is a natural case when you have attrition, right? You have different cohorts, and unless you really strictly assign this and or can use imputations, but still have some attritions that could be contributing to some power loss and during the estimation. Yeah, this the many questions I want to bring about, and then maybe some could be general, and but I want you to throw lights on the future of data science in political science or social science, and how these two cultures or two groups of methods could be bridged, could be learned from each other, and yeah, generally speaking, yeah.
Well, I think the promise of big data does not guarantee that we have a good design, right? Even if so, there's a lot of
causal part.
Here,
yeah.
there's a lot of discussion at Stanford, collaboration with industries, and in industries, actually, there's a new set of problems: how to run experiments. Experiments is relatively cheap to run, but how to run it effectively. And there's all kinds of but it's actually experiments are not easy. People think experiments are easy. It's not the case, with all kinds of interference and general equilibrium issues. But I think so there's, which opens a lot of opportunity. But they are less concerned about uncertainty because of the data abundancy. I think for us who from time to time maybe have access to big data, but most case are working with a couple thousand observations. These are nowhere near big data. We still worry about whether we have enough power to conduct hypothesis testing. But even with a couple thousand observations, some of the machine learning tools, like what you mentioned, lasso or for variable selection, or more non-parametric ones like random forest or generalized random forest.
Or like tree-based,
some lower level neural nets. They can also help, but there's actually, if you are interested, the audience are interested, there's a class offered by Stefan Wagger and Susan Acey. They co-taught a class called Machine Learning with Causal Inference with Machine Learning. The videos are all there, so you can watch them, so you can then keep yourself updated to the methodological development of this literature, which is very exciting, actually.
Yeah, much needed now. I think we have a couple of colleagues now could be offering the very important part of the causal models and causal inference in general. And Patrick is another one doing time series, and I think there will be another great inclusion and in our data science training. All right, then I think time is already out. And do we have more questions? Maybe one last question for Dr. Shu before letting him go. I think this is getting late in California too. Yeah, yeah. Okay. All right. Great.
Thank you for stay up with
really
me,
great.
people
Yeah.
in
Yeah.
Texas.
Yeah.
Okay.
This is
Just,
okay. I think it's
yeah, just a quick reminder. Just a quick reminder. I think Dr. Shu, you shouldn't be should be remind that people or audience can check back to your website, because
Yes.
we took a look at your website, and there are tutorials and also the softwares that you share with people on your homepage. So just a reminder that if the audience, any of you are interested, just please visit Dr. Shu's websites. It's at Yiqing,
yiqingshu.org.
Yiqing.org. Yes. Please visit the site, and then you should get a lot of things from there. Yeah. All right. And that's
Indeed.
just a
Indeed.
reminder. Carl.
Thank you so
All
much,
right.
both of you.
Okay.
Yeah, bye.
Oh, this is really gracious. Okay, thank you, Dr. Shu.
Bye.
Have
Bye.
a good
Bye.
weekend.
Good night. Bye. Good
All right.
morning or
Thank you.
evening. Bye.
Bye. And please check back next week, and we have another presentation. All right. Thank you. Yeah. And have a good night and have a good day.
Good night. Bye. Please be reminded our materials will be on our website and also our YouTube channel. And I posted on the chat box, and go to YouTube, look for DA Colloquium. Then you can get all the video and all the notes coming from the Colloquium. All right. Thank you. Thank you.
Yeah. Thank you. Thank you, Dr. Hall.
Thank you all.
And everyone. Thank you. Bye.
Bye.